So today we're going to optimize a 3D shape made from a 2D shape. So we're going to take a sheet of paper of a certain dimension and we're going to cut squares from the corners of the sheet of paper and fold it into a box. And what we want to do is make the largest box that can hold the most amount of things. In other words, we want to maximize the volume. So here we have a sheet of paper, which is, in this case, it's a 4 by 6. So there's a 4 and there's a 6. And what's going to happen is that we're going to cut 4 squares from the 2D, from the piece of paper, and then we're going to fold. So here we have 4 corners, and if we want to change from a 2D to 3D, what we're going to do is, as you can see, I'm taking the 2D and folding it into a box until it is closed, meaning the edges are together. So it's an open, when I say open box, meaning there is no top part, there is no lid on there. So we'll put this back down. And as you can see, there are certain dimensions of the box that we're going to have to calculate, which are connected to the flat sheet of paper. So because we're maximizing the volume, we know that we're going to have to create a function that's related to the volume of a box. So the volume of a box is length times width times height. So now we have 3 variables. So now we're going to have to either choose to express v in terms of L, or v in terms of W, or v in terms of H, or maybe v in terms of another extraneous variable that's connected to the L, W, and H. So let's actually label our values here first. So this is a 2D right now. So 2D, what do we know about this shape? Well, we know that the size is 6 by 4. So from here to here is 6, and from here to here is 4. And in order to create a box, a 3D box, we're going to have to cut corners, but we don't know the size of the boxes. So that's something that we don't know. So that means from here to here is X, from here to here is X. So there's a lot of X's going along here. So we cut them all, write them all out. So the next thing is, well, how do we somehow link the X's in regards to the length and width and height? So here we have the simulation of the box, and what we're going to do is we're just going to close it. And I want you to focus on the X's, so the corners of the box. If you notice the corners of the box, I'm just going to use a pointer here. So if you notice here, these are my corners, these are the X's. But when we fold them into 3D, they actually become the height of the box. So they become the height of the box. So in my diagram here, if I were to label this using the arrow, so this part here becomes the height. So the X is my height, and something happens to the width. Well, the width is from here to here, but we know that the whole thing is worth 4. So we're going to have to figure out this piece out by subtracting, so over up here. So the width is going to be 4 minus X and minus X. So from here to here is what we want, but we know that the whole entire thing is worth 4, and so this piece is going to be 4 minus 2x. So that's the width, and now from here, the length, which is from here to here, all right, we know that the whole thing is 6, but however, we're going to take off the x and the x from both ends. In other words, this piece here is 6 minus 2x. So in other words, my function is going to be expressed in terms of another variable that is indirectly or directly connected to the LWH. So in this case, what is my height? Well, my height is going to be X. I'll put that first. What's my width? My width is going to be 4 minus 2x. And my length is going to be 6 minus 2x. So this is the function we are optimizing. So the next thing we're going to address is the restrictions. What is the value for X? Well, based on the picture here, we know that we have to be able to cut out something. So that means X has to be greater than 0. However, what's the largest X that we can cut from here, but yet have a box? So there's a couple of ways to address this. I'm going to address this maybe using the function itself. So in other words, I want my volume to be positive. So I'm going to have to use the interval chart, meaning v of x is going to be greater than 0. In other words, x 4 minus 2x, and we're lucky it's already in factored form, must be greater than 0. We're going to do the interval chart. We're going to figure out the zeros. the zeros. This one gives me x equals to 0. This gives me x equals to 2. And this x equals to 3. I just skip steps. I just got the answer directly. We set our table here. I'm going to put in all the factors that are involved in the function. And I have 0, 2, and 3. And at the end, we get the following. So here's the following for our table. However, we need to look for the positive. So we have positive here, we have positive here, and we have positive there. Actually, this one should be a negative. This should be a negative. And it doesn't really matter because we need to have something to cut from x. So we cannot cut, for example, -1 centimeter. So this is not the proper interval. So we have two intervals. But the question right now is, are both of them valid? So this is where we have to actually look at the diagram. Look at the dimensions right now. So that's, in other words, would it make sense if you cut, for example, let's just say 5? Well, I don't think you can cut 5 because if x was 5, if you take off 5, but you can't because keep in mind, imagine taking 5 from here and 5 from here. It's impossible because the length is 4. You don't have 10 centimeters to take away from that side. So in this case, we're going to be focusing on this. Another way to address, to supplement this restrictions is the following. Well, I'm going back to the length, width, and height. I know for a fact that this length, or the height, has to be greater than 0. So x has to be greater than 0. This piece also has to be greater than 0, and this piece also has to be positive. So in other words, I'm going to take 4 minus 2x and solve for the linear inequality for each piece. If I do that and I solve it, I end up getting x is less than 2 and x is less than 3. So we have a bit of a conflict here because right now we got two inequalities. And you have to address the x's which are overlapping. So if you recall from advanced functions, when we have common inequalities, we want to find the one that overlaps. So the first one is 2 and this one is 3. So this one here will cover this ground. This one here in green will cover this ground, and you want to find an overlapping x restriction. In this case, it's going to be x is less than 2. So in other words, our restrictions is going to be less than 2, but above 0. So in my personal opinion, in regards to optimization, I think determining the restrictions is the most challenging part, aside from the development function. So just to briefly go through the algebra, so over here, I just recopied the question out again, and this is where you have to make the decision whether you want to expand or take the derivative right away. For me, I can expand really simple because it's a very simple quadratic multiplied by x. So expanding in my case, in my personal opinion, would be easier. I don't want to use the product rule if I don't have to. And then after that, I got the derivative, and then the rest is pretty simple, as in it's very calculus technical based, meaning you're going to set this to equal to 0. You don't need to set it to undefined because there's no denominator. Use your quadratic formula. You will get, I believe, 2 numbers from here. And out of those 2 numbers, those numbers have to fall within the restrictions. So make sure your CPs, make sure you have a y value, which you will because it's the domain is xr, yr. Make sure that your critical points is within your restrictions before you test it out in your first derivative test. You have an option if you don't want to do first derivative test to check whether it's a max or min. You can always do the second derivative test. So in other words, you would take your second derivative, which is -28 plus 12x, and you would sub in your critical point in there to see whether it's positive or negative. If it's negative, then it's going to be sad face, meaning it's going to be a max. And if it's a happy face or concave up, it's going to be a minimum. And then after that, don't forget to check your n behaviors, or your n, let's call it the n behaviors, or I don't want to call it endpoints because these are not, x 0 and 2 are not part of it. So in other words, check the limit as x approaches 0 from the right and see what happens to the volume. Check the volume as you approach 2 from the left of the volume. In this case, you just simply sub in 0 into here. You're going to get a 0. You sub 0 into the function, you get a 0. And don't forget, you should check always what exactly is the maximum volume. So make sure you put your CP and figure out what the actual number is, and then you're done.